Okay, so let's go ahead and get started. So first, just an administrative announcement. So I am actually going to be out of town next Tuesday, which is, I believe, October 14th. Given that it's just the Tuesday after the holiday, I thought I might just cancel class since I imagine other people will be out of town as well. So probably what I will do is propose some makeup class some later time in the semester. Do people have a particular... Actually, maybe what I'll need to do is check on room availabilities. But one possibility is that we could just go a little later into the December. Another possibility is that we could do a Wednesday or a Friday or something, or a Monday or something like that. Do people have preferences? Like if I wanted to schedule, say, a makeup class on Wednesday at 4, say, would that be okay with everyone? What's that?
There's quantum theory.
You have quantum theory at the same time. Monday at 4? Monday at 4 is probably the same time. Friday at 4? Friday at 4 is good. Okay, so maybe that's what I'll try and do. I'll send out an email when I try and get this thing scheduled. Okay. Okay, let's go ahead and do some physics. So today what I want to do is continue with our discussion of path integrals in quantum mechanics and quantum field theory. And what we'll do is we'll see that the path integrals give us a rather different and rather elegant way of deriving the Feynman diagram expansion, which allows us to perturbatively compute observables in quantum field theory. And in particular, we'll see that it gives us a completely different derivation of exactly what we derived using a rather different method, namely the Schwinger-Dyson's equations, last week. Okay. So just to remind you of what we learned last week, so we saw that in quantum mechanics, if you want to compute the expectation value of some observable, let's say the matrix element, so the expectation value of a product of observables, say if capital Q is the operator that measures the position of a particle, then if you want to compute the expectation value of a bunch of position operators at times t1 up to tn, sandwiched between some initial and final states, then you do this by computing a path integral where you integrate over all possible paths that a particle could take. That is to say, all possible functions q of t of the exponential of the action, e to the is, over h bar. And if one wants to compute the expectation value of some operators, q of t1 up to q of tn, then all you do is insert in the path integral the value of the function q at times t1 up to tn. And the point of the path integral is that we've replaced this expression on the left-hand side in terms of operators in terms of an expression on the right-hand side only in terms of these functions q. So there's no operators, there's no Hilbert space appearing explicitly anywhere in the path integral formulation. But those quantities that we can observe, namely correlation functions, are still computable using either the Hamiltonian or the path integral formulation. Okay. And the initial and final states are imposed by the boundary conditions on the path integral. That is to say, we constrain the set of functions q of t that we integrate over so that q at t initial is q initial and q at t final is q final. Okay. And we also learned that there was an analogous integral where we integrate not over all paths through configuration space, that is all functions q of t, but there's another formulation where we integrate over all possible paths through phase space, that is all possible positions and momenta of the particle. So this is an integral dq dp of the action, which, if we think about it in the Hamiltonian formulation, is I times the integral of p q dot minus the Hamiltonian. So here I'm using the fact that the Lagrangian is pq dot minus the Hamiltonian. And we have the insertions of q of t1 up to q of tn. Okay. Now, at the end of last class, I introduced a very clever and rather sneaky trick which allows us to compute these time-ordered expectation values in the vacuum state in a very clever way. Okay. So basically, if we're interested in the vacuum state, we can use the fact that if you replace the Hamiltonian by 1 minus I epsilon times the Hamiltonian, where epsilon is some real number, and you acted that on any state, then you could see that as t goes to minus infinity, this just picks out the vacuum state. So here I'm choosing my energies such that the ground state has 0 energy, the vacuum state has 0 energy, and all of the other states have positive energy. Okay. So you can see that as t goes to minus infinity, this thing goes like e to the minus th, sorry, e to the plus th, because we have an I epsilon h. So this term at the epsilon gives you an e to the plus t epsilon h, which at t goes to minus infinity vanishes except on the state where the Hamiltonian is 0, that is to say the ground state. Okay. Likewise, if you were to take this time evolution operator modified by the insertion of 1 minus I epsilon and act on a bra vector rather than a ket vector, you would also just get the vacuum state now at t goes to plus infinity. So you can see that if you're interested in studying the correlation functions of some set of operators in the vacuum, and you take t initial to minus infinity and t final to plus infinity, we can compute the vacuum time-ordered expectation value simply by performing this analogous path integral, except with the replacement that the Hamiltonian is replaced by 1 minus I epsilon times the Hamiltonian. Okay. Or, since the Hamiltonian is positive, this is effectively the same as adding a small imaginary part to all of the energies. Okay. And so this magically will project us onto the ground state. Okay. The only subtlety in this expression is that I really shouldn't draw an equals sign here. I should draw a proportional to sign there. Okay. They're only proportional because we have neglected these factors, say, here and here, that arise because you have to take into account the fact that whatever initial state you started with might have some overlap with the vacuum that is some number that we're not keeping track of here. Okay. So what we conclude is that if you're only interested in studying vacuum expectation values, then all you need to do is add a small imaginary part to the Hamiltonian, and then you're all set. Okay, you don't need to worry about imposing initial and final boundary conditions on your fields at t goes to plus or minus infinity. Okay. Essentially, taking the energies to have a small imaginary part automatically imposes these boundary conditions for you. Question? Yeah, all I did is I tried, unless I made a mistake, all I did is I rewrote this equation, except where I added a factor of 1 minus I epsilon here. Since. Yes, I should have done... No, yes, I should. Thank you. Yes, I guess I should. Do I actually want to do that? I mean, what I really want to do, yeah. This gets into a sort of thorny issue. Yeah, no, I don't think yeah, I don't think I do want to. I do want to put a minus sign there, right? You know, because I'm just imagining that I have some operators that I'm taking expectation values of, and they're evolving by time evolution in the usual way. Let's see. And no, I guess that's right. You would get an e to the minus I t appearing there. Yeah, so for example, if you had some operator q, it would evolve the e to the minus I ht q e to the plus I ht. So you're right. There should be a minus sign there, yes. And indeed, you can see that will give you an overall factor of e to the minus t epsilon h, which as t goes to plus infinity will vanish unless h is equal to 0. Now, I'm doing something a little slick here, which is that I have not complex conjugated that quantity right there. And the reason is really that once we make this replacement, h goes to 1 minus I epsilon h, I'm no longer taking the Hamiltonian to really be a Hermitian operator. Okay. I mean, so that's the slightly confusing thing about what I'm doing. At this point, you could just imagine this as a formal replacement, where the Hamiltonian is replaced by Hamiltonian times 1 minus I epsilon times the Hamiltonian. Okay. And as we mentioned at the end of the class last time, this is equivalent to taking t to some modified time coordinate, where we rotate it by a factor of 1 minus I epsilon. Okay. So, in other words, this is just a different choice of integration contour in the complex time plane. Okay. So, in the complex time plane, instead of integrating along the real axis, as is traditional, we would integrate along some axis that looks like this. So that's the t tilde axis. Yes?
So are we going to trust this trick, or are we going to fix it later on?
What we're going to discover, possibly by the end of this class, is that this trick is something that we have already done before in this class. Okay? And in fact, the name epsilon here is not an accident. This is the same I epsilon that we encountered when we worked out the contour manipulations that were necessary for defining the Feynman-Green's function. Okay? So, in fact, this trick, not only, right, you might worry about the validity of this trick. Okay? That's perfectly reasonable. But in fact, we've already derived this trick. Okay? When we use the contour argument to, when we introduced an I epsilon to pick out certain poles that we include in the contour of integration when we defined the Feynman-Green's function, we'll see that this is in fact the same I epsilon. This is the same thing. Okay? So if you like, you don't have to use this trick. So I derived Feynman diagrams for you without using path integrals. Okay? I introduced the I epsilon in the propagator just by staring at the contours integrations that were necessary to define the Feynman propagator. And that I epsilon was just there. Okay. And we're going to see that, in fact, this I epsilon is the same as that I epsilon. Okay. So all I'm doing here is, All I'm doing is presenting, if you like, a different derivation of things that we've already understood once in this class so far.
How could the Hamiltonian is not Hermitian, we compensate somehow?
Well, at the end of the day, in the path integral formulation of quantum mechanics, you don't deal with operators. You don't deal with Hermitian or non-Hermitian operators. You just compute correlation functions. Okay? And at the end of the day, the H that is appearing here, it's not Hermitian because it's not even an operator. It's a function of P and Q. Okay? So one doesn't really need to worry about whether it's Hermitian or not. You should worry about whether it's real or not. And indeed, it's not real because we've introduced explicitly those pieces by hand. But it's not real in exactly the way that we want it to be not real. It's not real in exactly the way that is necessary in order for us to not worry about these boundary conditions. Okay? If this makes you uncomfortable, don't worry about it too much. If you like, you could think about everything derived from the non-path integral point of view. And we already derived the Feynman diagram rules using the Schwinger-Dyson equation. But you're going to see that it's much, you'll be much happier if you believe in Feynman, in path integrals. Okay? You'll be much, it gives you a much nicer way of organizing your thinking about these sorts of things. Good. Okay. So what this means, so if I just make this replacement where t goes to t twiddle, whatever you call it, then what that means is that I can just think about this time-ordered expectation value as being computed by a perfectly standard Feynman path integral with the only difference being that this action that appears here is now the slightly changed action where all of my time derivatives have now become derivatives with respect to t tilde, and my dt integral in the definition of the action is a dt tilde integral. And the final subtlety that we need to worry about is the fact that we only had this proportional to sign here, which arose because we were neglecting all of the normalization factors. So I'm going to fix that up just by normalizing everything by hand, so that I'll just divide by the norm of the vacuum state here, okay, otherwise known as just the path integral e dq e to the I s over h bar with no insertions. Okay. So this is to keep everything normalized. And this is the basic formula that we're going to be using when we begin our discussion of the path integral approach to field theory. So, in particular, in quantum field theory, all we do is imagine replacing the path integral over the set of functions q of t to an integral over the space of all field configurations phi that depend both on x and t. If you like, you could imagine that you have a path integral in quantum mechanics where you have n degrees of freedom that are labeled by an index I that goes from 1 up to n. And then you could imagine those degrees of freedom being, say, the value of the field phi at a bunch of different points in space, say at a lattice of points in space. And then you could take the limit where those lattice points get closer and closer and closer together. And then in that limit, where n goes to infinity and the lattice becomes infinitely close, you'll reproduce this integral where you integrate over all field configurations. So this is an integral over all field configurations. That is to say, all possible values of phi as a function of x and t. So now our goal then, is to define an efficient algorithm for the computation of these vacuum expectation values, these time-ordered vacuum expectation values, which are the normalized integrals over all possible field configurations. So that's what we're going to do this class. Before I do so, let me just pause and see if there are any questions.
Are you taking the detail in which t is to infinity to get the vacuum?
That's right. So what I really want to do, so notice that in order for this Euclidean continuation trick, this I epsilon trick to work, I really have to take t to initial to minus infinity and t final to plus infinity.
The action.
That's right. That's right. So the action is really an integral dt from minus infinity to infinity. Or really I should call it an integral dt tilde from infinity times 1 minus infinity times 1 minus I epsilon to plus infinity times 1 minus I epsilon. At the end of the day, we're going to often conveniently forget about these I epsilons until we need to remember them. In fact, for the time being, at least for the most of the rest of this class, I'm not going to focus too much on these I epsilons. They will only make one brief appearance later on in this class, a cameo. Any questions before I continue? Okay. So, an efficient way of packaging these vacuum expectation values is by introducing what's known as the partition function or generating function of a quantum field theory. So the generating function of a quantum field theory is defined as follows. So the idea is that rather than computing an infinite number of vacuum expectation values, where I have a bunch of insertions of this field operator phi, what I want to do is introduce one function that I'll call z of j. That's a functional, so it depends on another function, j, referred to as the source, which is defined as the integral d phi of e to the is plus I times the integral d4x of j of x times phi of x. Okay. So this is just some functional. It depends on something that I've called j of x. And why is this thing useful? Well, this thing is useful because if you imagine expanding order by order in j of x, then its expansion includes all of the time-ordered correlation functions that we're interested in computing. So in particular, the leading term at order j to the 0 is just the vacuum expectation value with no insertions. The first term is the vacuum expectation value with one insertion. Okay. And so on and so forth. The next term would be a vacuum expectation value with two insertions, integrated against two sources, and so on and so forth. Okay. So that means that if we can compute this generating function z, then we have in one fell swoop computed all of the possible time-ordered expectation values in the theory. So this generating function includes all possible expectation values. And the way that you would extract an expectation value, let's say you're interested in computing the 4-point function, you would just take the z and expand it to fourth order in j. So there's a sort of slick language that we use to encapsulate that statement, which is the language of functional derivatives. So in particular, if we define a functional derivative, so the functional derivative is supposed to be the natural generalization of the partial derivative to functions. So we define the functional derivative. So if you have some functional of j and you take its functional derivative with respect to j of x, then, well, the simplest functional of j would be the function j evaluated at some other point y, and the derivative of that functional is just going to be defined by the delta function that sets x equals to y. Okay. And then, so that's the basic functional derivative. And more complicated functional derivatives are then defined by the chain rule, the usual chain rule of calculus. And in one of the exercises on your problem set, you're going to verify that this functional derivative is really identical to the usual partial derivative of multivariable calculus, except where instead of a finite number of variables, when you have partial derivatives, you have an infinite number of variables, one for each point in space-time. And moreover, I believe, if I remember correctly, on your problem set, you're also going to verify that with this definition of the functional derivative of the action functional with respect to a field phi is indeed the usual Euler-Lagrange equations. So this definition of the functional derivative is consistent with our notation that the equations of motion, the Euler-Lagrange equations, are the variation of s with respect to phi using this functional derivative notation. Okay. So why is this useful? This then is useful because if you remember that z is the integral of e to the is plus the integral of j of x phi of x dx, then the functional derivative of z with respect to j of x evaluated at j is equal to 0, then all that functional derivative does is it brings down 1 power of phi of x. So I guess I had an I here in the definition. So what I'll do is I'll put a minus I here. So this brings down just 1 power of phi of x. Okay. And so this then is, so then we can see that the time-ordered vacuum expectation value of a bunch of field operators is given by a bunch of variational derivatives of the generating function z evaluated at j equals 0. And the normalization constant, where we divide by the norm of the vacuum state to keep everything normalized, just says we put an overall 1 over z out front. Okay. So is this clear, more or less? Any questions? So in fact, if you think about it, these derivatives do commute. Is that? Yeah, okay. I guess that wasn't an explanation. That was merely an instruction that they do commute. But they do. Okay. Partial derivatives commute with one another. Okay. And indeed, if you think about it, these derivatives are going to commute with one another as well. And indeed, because of this time ordering symbol here, the order in which you insert these various x's can't matter. And I suppose what I need to do also here is put a factor of minus I to the n out front, because I had this I here that I need to cancel, which was that minus I there. Okay, so let's go ahead and compute this guy. So first, let's consider the example of free quantum field theory. So the basic idea is actually very straightforward. The basic idea is the following. So in a free quantum field theory, the action is just the integral d4x of minus 1/2 of 1/2 d phi squared minus m squared phi squared. What I'm going to do is integrate that by parts so that the action looks like this. So I've just neglected an overall total derivative, so a boundary term. And then this generating function is the integral d phi times the exponential of minus I over 2 times the integral d4x phi of x times this Klein-Gordon operator acting on phi of x plus I times the integral d4x j of x phi of x. Okay. So the basic idea is the following. Let's just pretend that phi, instead of being an infinite number of variables, one for each point in space-time, was just a single variable. Okay? It was just some number phi that you were computing. Then this is a Gaussian integral, and we know how to do Gaussian integrals. Okay? And if you don't know how to do Gaussian integrals, then do your problem set, because you'll have to learn how to do Gaussian integrals if you don't know it already. So the idea then is that if you had, say, the idea is that if you think about this as an infinite number of Gaussian integrals, each one of them you can do, then you can actually solve exactly for this generating function z of j. Okay? And that's exactly what we're going to do. Okay? So morally speaking, okay, you want to think of this term here as so let's say that you have, instead of an infinite number of variables phi of x, you have a finite number of variables that we were calling qi. Then this would be something like qi qj times aij, where A is some matrix. And this would be something like the sum over I times qi ji, where here you could think, again, as we were thinking about it earlier, as I being a label that goes from 1 up to n, and qi is the value of the field phi at some point in space. And then this is just n Gaussian integrals, and we know how to compute these sorts of Gaussian integrals. Indeed, the Gaussian integral, you have a finite number of these variables, and you have a matrix A of this form, is exactly one of the problems that you'll be computing on the problem set for this week. And roughly speaking, what is the answer? Well, this is roughly an integral of this sort. Okay. And the answer is found just by basically completing the squares. And it's basically something quadratic in J with the inverse of the operator A here. So this is something that I believe you'll show on your problem set for this week. Don't worry, we'll do it out explicitly for the infinite dimensional functional integral right now. But the basic idea here is that when we do this functional integral, by thinking about it as an infinite number of Gaussian integrals, the thing that's playing the role of that matrix Aij is the operator d squared plus m squared. So the operator d squared plus m squared, the Klein-Gordon operator, is thought of as a matrix. And the guy that's appearing right here is the inverse of that operator. So what is the inverse of the Klein-Gordon operator? Well, it's the thing that if you act on it with a Klein-Gordon operator, you get 1. Otherwise known as the Green's function for the Klein-Gordon operator. Otherwise known as the propagator. So just by sort of guesswork, we can already sort of anticipate what we expect the answer for this generating function to be. So now let's try and verify this and work this all out a bit more explicitly. Maybe before I do so, let me pause and see if there are any questions. Okay. So the first thing that I want to do is I want to move from position space to Fourier momentum space. I want to do a Fourier transform to work in momentum space. The reason being that this operator d squared is something that looks sort of complicated in momentum space, but it looks simple in Fourier space. In particular, it's diagonal in Fourier space. So let's introduce the Fourier transformed variables. So if I have a function phi of x, then I'll define the Fourier transformed variables phi tilde of k in the usual way by integrating with this Fourier transform. And likewise, phi of x can be written in terms of the Fourier transformed variables by integrating, let's see, we need a minus sign somewhere. The Fourier transformed variables d4k. You know, there are various conventions that go into introducing these Fourier transforms. Sometimes people don't put all of the 2 pi's there. Sometimes people divide up the 2 pi's between in some different ways. Sometimes people put different signs there. It's all just a matter of conventions. But the idea is that what we're going to do is we're going to do a change of variables in our path integral, where instead of integrating overall the functions phi of x, we're going to integrate over the Fourier modes phi tilde of k. And the point is that this is nothing more or nothing less than the standard sort of change of variables that we always do when we perform integrations. Okay. So you can see here that phi of x is related to phi tilde of x in some linear way, by some linear operation. And so when you perform this change of variables, the integral d phi of x is going to be the same as the integral over all the Fourier modes phi tilde of k, up to some Jacobian factor. Okay. That Jacobian factor, well, as usual, I'm not really keeping track of overall constants out front of the integral, so I'm just going to forget about it. At the end of the day, I'm going to have to divide out by this generating function at j equals 0 anyway, so I really don't need to worry about that Jacobian factor. And so let's go ahead and rewrite this integrand in Fourier space. Yes, question? So let's put it this way. The Jacobian, but this is a linear change of variables. Okay. So it's just like if you had some set of variables xi and you were doing some change of variables, let's call it ji, j, xj. Then, you know, dxi would go to the determinant of j times the dxj's. But the important point is that determinant is independent of the x's. So it's just some overall number out front. Okay? That's why it's important that it's a linear change of variables. We could always imagine doing a more complicated change of variables, but that would involve introducing some non-trivial Jacobian. Okay? When we study quantum gauge theories, indeed, that's exactly what we'll need to do. And in fact, just a historical note, the reason why we all study the path integral formulation of quantum field theory is that, in fact, that is the only way that we know how to think about certain gauge theories. You know, there are certain non-trivial Jacobian factors that arise when we do changes of variables in the path integral. Okay? This is just a particularly simple change of variables. So again, if you want to think about this a little bit more prosaically, you could imagine discretizing space, and so that the integral d phi here would be, you know, a product over all values of the spatial variable times d phi of x. So, and that would then correspond to some discretization of the allowed momenta. And so this would really be a finite change of variables and a discrete Fourier transform rather than a continuous Fourier transform. Okay. So what we now need to do is figure out what the action is in these Fourier transformed variables. Well, that's straightforward enough. I'll just take this expression for phi and plug it into my expression here for the action. So what you get is an integral d4k and an integral d4k prime, and that integral d4x. We get a phi of k. So, well, we get those two Fourier transform factors. So we get an e to the minus I x times k plus k prime. And then we get a phi of k and a d squared plus m squared times phi of k prime. Okay. So the first thing to notice, sorry, I was a little sloppy here. The first thing to notice is that I wrote down slightly the wrong expression here. So I should write this as e to the minus ikx phi tilde of k times the derivative operator acting on e to the minus I k prime x phi tilde of k prime. And that derivative operator just acts on this term right here, and it just brings down a factor of minus k prime squared. And then you're left with an e to the I kx times an e to the I kx prime, which is a delta function that sets k equals to minus k prime when you integrate it over x. And you can then use that delta function to do the k prime integral. And so you're just left with an integral d4k of phi of k times minus k squared plus m squared times phi of minus k. And similarly, the other term that appeared in the integrand was the source j of x times phi of x. And that's just going to be the integral d4k of j of k times phi of minus k. And I've been a little sloppy. I've been forgetting my tildes. So those are all tildes. And here, j tilde is the Fourier transform of j of x. Okay. So just to summarize, our partition function z is going to be the integral over all of the Fourier modes times the exponential of minus I over 2 times the action d4k phi tilde of k. Let's pull out that minus sign and write this as a k squared minus m squared phi tilde of minus k. And then we have a j tilde of k times phi tilde of minus k. And what I'm going to do is I'm just going to write this all a little bit more symmetrically. I'm going to write this as an integral d4k. I'll pull that 1/2 out front. I'll put that I in right here. And, okay, I didn't need to write two d4ks here. Plus j tilde of k phi of minus k plus j tilde of minus k phi of k. Okay. That's just to make everything look a little bit more symmetric, so that my integrand here is symmetric under k goes to minus k. Okay. All I did here is I did the trivial thing where this is 1/2 integral d4k, j of k, phi of minus k, plus j of minus k, phi of k. Just by doing the dividing into two terms and doing the change of variables k to minus k in the second term. Okay. Now, the point here is that this integral here is really an integral over, it's really an integral over the product of all different momentum modes of each one of the Fourier modes phi tilde. So I want to think about this integral really as literally the product of each one of those Fourier modes. And so you can see now that this is literally just the product of an infinite number of Gaussian integrals. Because the exponential of a sum is a product of exponentials. So this is equal to the product over all momentum modes times the integral for a given momentum mode of this guy e to the minus e to the 1/2 phi tilde of k times I k squared minus m squared phi tilde of minus k plus j tilde of k phi tilde of minus k plus the same guy where I've written everything so that it's invariant under k to minus k. So now this is just a Gaussian integral, and I can just do it. And how do you do a Gaussian integral of this sort? Well, the important trick is that you don't do Gaussian integrals of this sort. You complete the squares, and then you don't actually ever bother to do the original integral. Okay? So, in particular, what we do is we introduce a new variable. I'll call it chi, where we just shift this Fourier transformed variable by j over, let's call it k squared plus m squared. Oh, I'm sorry, there's some i's here. Okay. And when you do that change of variables, so first of all I'm doing is shifting phi when I do this change of variables. So that doesn't change the integration measure. So this partition function, this generating function, is the integral, well, let's call it the integral over all of the chi's. Here, let me write out the product over momentum modes separately. It's the product over all momentum modes of the integral over all chi's times the exponential of, well, I chose this term here to complete the squares, so that I'll get something that is quadratic in the chi's, and then you have a term left over from completing the squares, which, let's see if I've done everything correctly, is quadratic in k and goes like k squared minus m squared. Okay. Looks like I got a minus sign. So that just comes from completing the squares. So that tells us, so the important thing to notice is that this second term here is completely independent of the chi's. So we can remove it from the integral. And so the generating function z is just going to be the exponential of I over 2 times the integral d4k, j of k, j of minus k, over k squared minus m squared, times the integral of all those chi's. That's just an overall number. We don't care about overall numbers. It's independent of j. We're going to divide it out anyway. So we just don't need to keep track of it. Or if we want to write this in position space, this is the exponential just using the fact that j of k is the integral d4x of e to the I kx, j of x, I guess with a minus sign there. This is just the exponential of 1/2 times the integral d4x, the integral d4y, we get 2 x's and 2 y's for each of the j's, times j of x delta of x minus y, j of y, where delta of x minus y is the integral d4k of e to the I k x minus y times I over k squared minus m squared. Hopefully that's at least a little bit familiar. This is just the Feynman propagator. And we can now see where our friendly I epsilon is going to come back to pay a visit. So far, I've been sort of sloppy about keeping track of that I epsilon that arose when we projected onto the vacuum state. But remember that I epsilon was only there to remind us that whenever we have an energy, we shift it to be an energy plus I epsilon. And this denominator here, k squared minus m squared, that's just the Hamiltonian of a free particle. So that means that that I epsilon just has to go in the denominator there, because we have to shift the energies by an I epsilon. Okay? So this is to project onto the vacuum state. So what we see here is that we have completely solved a free quantum field theory just by explicitly computing the path integral as an infinite number of Gaussian integrals. And what we found is that in a free quantum field theory, this generating function is just the exponential of j of x, j of y, connected by a propagator. Or, if you wanted to use the language of Feynman diagrams, what we could do is introduce another symbol to describe a source. So Each source will be denoted by a dot, a solid dot, and then the statement that we connect two dots by a line is the statement that those two sources are connected by this propagator here. So each dot here represents an integral d4x of j of x, and this propagator represents, well, this line represents the propagator d of x minus y. Okay. So, for example, if you wanted to compute the two-point function, 5x1, 5x2, time-ordered in the vacuum state, this is just minus I squared times the derivative with respect to x1 and j of x1 and j of x2 of the partition function. Okay. Sorry, I keep calling the generating function the partition function. I keep calling it that because it is the partition function, but that's not what I'm calling it now. So every time I say partition function, in your heads do a find replace and call that a generating function. Okay. And what is this generating function? Well, it's the exponential of this quantity here. So if we want to just understand that explicitly, let's just expand it out. Let's just expand out that exponential. So that's 1 plus 1/2 times the integral d4x, d4y, j of x, j of y, delta of x minus y, plus higher order terms in the exponential. All of those higher order, then this is evaluated at j is equal to 0. All of those higher order terms in the exponential will just vanish because we're only hitting them with two derivatives, so that just kills two factors of j. All of the higher order terms will be higher order in j. Okay, so those will vanish when you set j is equal to 0. So this is just the propagator, x1 minus x2. And there's no factor of 2 here because there are two different ways that these derivatives can act, that d by dx1 could act either on this guy or on this guy. And so those two different ways cancels this factor of 2 right here. So we've re-derived, from the path integral point of view, the propagator of a free quantum field theory. And in this way of doing it, it is immediately clear how to generalize this to higher point functions. So more generally, z of j being e to the 1/2 times this propagator allows us to expand this to get all of the various different possibilities that appear in Wick's theorem. So for example, you get 1 plus the two-point function, and then the terms that are quartic. Well, but you could work them all out if you like. They're all of the higher order terms. So I guess we could just write this as 1/2 plus, let's say, 1/4 times 2 factorial times this guy squared plus dot 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 will give all of the possible Wick contractions that appear in Wick's theorem. So, for example, in general, you can show that a time-ordered expectation value of a bunch of free fields is the sum over all possible pairings of the product of the free propagators. Okay. The sort of lovely thing about these generating functions is that a fancy statement about the sum over all possible pairings is simply encapsulated in the statement that z of j is the exponential of this two-point function. Exponentials are very convenient for keeping track of combinatorics like this. So whenever you have combinatorics that involves summing over all possible permutations of something, all possible pairings, things like that, then you can often resum that up into an exponential. We'll see that again, probably not this class, but next class. Any questions before I continue? Yes.
The function g of x, doesn't represent that it is
Well, I called it a source because, well, it represents a source. Okay. Because what is j of x? Well, we introduce j of x by saying s goes to s plus the integral d4x j of x phi of x. So if j of x is non-zero, then what that's doing is it's saying that will lead to, for example, the one-point function of phi being non-zero, which means that there's some sort of classical source for the field phi. Okay? So for example, if you wanted to study particle creation by a classical source, then you would study the z of j with j being non-zero. This is not just an abstract example. When we come to electromagnetism and gauge theory, this is explicitly what we're going to be doing. Okay? In that case, in gauge theory, we'll introduce terms that look like integral d4x of a mu, the four-component electromagnetic potential, times the source j mu. Okay. And then, as you saw explicitly, I think, in the second problem set, adding a term, the integral a mu j mu, to the action explicitly added a source term to Maxwell's equations in the classical equations of motion. Okay. So that led to the source term in the classical Maxwell equation that looked like this. So yeah, for the scalar field, that would lead to an extra term in the equation of motion that looks like this. Okay. That would be the analog of having a source term in the Klein-Gordon equation in the same way that having some charges gives you a source term in Maxwell's equation. Okay. Yes? I wouldn't say it's adding, when we say an interaction, usually what we would mean is adding another field to which it interacts. This is not another field in the sense that j is not a dynamical variable. There's no, we're not integrating overall sources j of x in the same way that we would integrate overall field configurations phi. So j is not a dynamical variable. It's what we would call a background source. So, for example, if you wanted to study the properties of electromagnetism in the background of some charged object, and you wanted to keep that object fixed, you didn't want to study its dynamics, you just wanted to hold it still and study the electromagnetic field in its background, what you would do is you'd write down the current j mu coming from that object, you would put it into the path integral, and then you would start computing with fixed j mu. Okay. Now, if you wanted to add that object's dynamics, then you would start considering the dynamics of the sort of constituents of that charged object, for example. So, yeah, so I called it a source for precisely that reason. Okay. Good question. Was there another question? Okay. Good. Okay, good. What about interacting quantum field theory? Okay. So let's now consider interacting field theory. And so let's consider our old friend the phi cubed theory. It's the simplest example. So that means that in addition to the kinetic term, I'll take an interaction term that is 1 over 3 factorial times the coupling constant times phi cubed. And again, we are interested in computing the generating function where you integrate over all fields of e to the is plus the integral of j times phi. And what I would like to do is separate this out into two terms. I'll call this L0, and I'll call this L interaction. So what do I not call that L0? I'll call it L free, because it's a free Lagrangian, and I'll call that second term the interaction term. So this is the integral d phi of the exponential of I times the integral d4x of the free Lagrangian plus the interaction term plus the source term. So let's now imagine studying this when the coupling constant g is very small. In that case, what we would do is we would expand the exponential. You would have an e to the I integral of g times phi cubed, and you would write that as 1 plus g, the integral of g times phi cubed, plus 1/2 times the integral of g times phi cubed squared, plus so on and so forth. Just expanding out that exponential. And each one of those terms in that expansion could be computed using the free quantum field theory expression for the generating function that I wrote down above, where each time you bring down a factor of phi, you just need to take a derivative with respect to the source, j of x. So what that means is that I could actually rewrite this generating function as follows. I could rewrite this as the integral of the exponential d4x of this interaction term, but every time I have a phi of x in that interaction term, I'll just replace it by a derivative with respect to the source j of x. And I have to compute that in the free theory, so I have an integral d phi of the exponential of I times the integral d4x of L free plus j phi. But that path integral I know how to do. I've already done that path integral. So this is the exponential of I times the integral d4x of the interaction terms times the free answer, which was the exponential of 1/2 times the integral d4x prime j of x delta of x minus x prime j of x prime. So is it clear what I'm doing here? What I'm doing is, in the interaction term, I imagine just computing that by calculating expectation values in the free theory. So the point is that every time, the basic point, this is what we really argued up here. Let's see, where did I write it down? This is the point, that every time you want to bring down a factor of phi of x in this path integral, then all you need to do is take a derivative with respect to j. Okay. So here, let me just write that out. Explicitly say, so since if you take a bunch of derivatives of the generating function of the free theory, you just get the integral d phi of e to the I, so it's the integral of L free plus this interaction term, sorry. So let's just say evaluated at j equals 0, or I guess we don't even need to evaluate it at j equals 0. You just get the integral with this interaction term of the insertion of a bunch of phi's. Okay, is that clear, more or less? Every time you have a phi of x that you want to add to this, so you take this path integral here, and then just imagine expanding out in powers of L interaction. That'll bring down some number of phi's, and the way that you get those phi's is you take derivatives of the expression without phi's with respect to j. Any questions on this? If this is not completely clear, what I'd encourage you to do is take this exponential, expand out the first couple terms, and compare it to what you would get here. Okay? The point is that every time you take a derivative with respect to j, you pull down a factor of phi. I get a couple blank. I'm getting some blank looks. Should we do this a little bit more explicitly, or shall I continue? Okay, a little bit more explicitly. Okay. So in particular, let's start with the integral d phi of the exponential of I times the integral d4x. Let's call it L free plus j phi plus, let's call it g phi cubed. So what is that? Well, let's write this as the integral d phi times e to the I, let's just call it s naught plus j phi, just to keep my notation a little simple. S naught being the action of the free theory, and I'm just forgetting about that integral sign there, because if I write down my integral signs, it'll take all day. Then what do we have? We have 1 plus the integral of g times the integral of phi cubed plus 1/2 g squared times the integral of phi cubed squared plus dot dot dot. And the point was that because of this expression here, we could write this as 1 plus g times the integral d4x of d by d j of x cubed plus dot dot dot, acting on the integral d phi of e to the I s naught plus j of phi. Okay, and then I could take this term and I could resum it and rewrite that as the exponential of g times, sorry, I should call it the exponential of the integral d4x. And I guess I forgot my i's here. Okay, so there's some i's here. Of g times d by d phi of x, d by d j of x cubed. Is that a little more clear?
Before you're writing the L int as a function of that function.
Yes. 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 Good. Thank you for asking that question. Yes. That is important. L int is a function of phi, and every time I have a phi, I replace it by a d by dj of x. Okay. I apologize if that was not clear. Is that why I was getting so many blank looks? Okay. Yes, that is why I was getting so many blank looks. Yes. So, right. I mean, the important point is that I brought this guy out of the integral. There's no such thing as phi outside of the integral. Phi is a variable that you are integrating over. Okay. What I'm doing is replacing in my interaction Lagrangian every phi by d by dj. Okay, much better. Are there any questions on that? Okay, and now Feynman diagrams appear like magic. Because what do I do? Let's take that expression there. So I have an exponential of this function that involves a bunch of derivatives with respect to j, and I have an exponential of something which has a bunch of j's in it. Okay. So all I need to do is start expanding out and acting these d by dj's on these j's over here. Okay. So I'm just going to start out by expanding out those exponentials. So let's first expand out this exponential. Okay, I'll write it as the sum as v goes from 0 to infinity, 1 over v factorial. So let's do the explicit case where I have a cubic interaction. So I have an I over 3 factorial times g times the integral d4x of, what was it, minus I d by d j of x cubed, and we take all of this to the v power, and then now let's expand out this second exponential. I'll write that as the sum over p from 0 to infinity of 1 over p factorial times 1/2 the integral d4. Let's call these variables d4y and d4z so we don't get them confused with the d4x's here. We have a j of y times this propagator times a j of z. Okay. So now what I would like to do is to start thinking about terms in this sum. And I would like to associate a diagram with each one of these terms in the sum. And in fact, my choice of these variables p and v is not an accident, because v is the number of powers of the coupling constant g that appears. So it is going to be the number of vertices in the Feynman diagram. P is the number of powers, sorry, there's the pth power, of course, the number of powers of the propagator that's appearing. So P is the number of propagators. Okay. So each term is represented as a diagram with v vertices, each with a coupling g, and p propagators, each with, sorry, I'll call them p lines. Okay. Each with a propagator delta. And each of these diagrams will also have some number of j's which describe external sources. So I'll label them by E. And so the number of j's will be 2p minus 3v, or minus 3v. Because each time you have a p, you get two external sources here, two j's, and each time you have a v, you remove 3 of them by taking derivatives. Okay. And so what I'll do is I can now write down my Feynman diagram expansion for z of j. So each diagram has a bunch of external sources which, as above, I'll represent by a solid dot, okay, which in equations will just be an integral with some source, j of x. It'll have v vertices represented by a trivalent vertex for a cubic theory, which is ig, and we have to integrate over the location of the vertex, okay, which I'll call x here, and we have p propagators. So each of those I'll represent by a line, which is just going to be the propagator between the 2 points, the 2 endpoints of the line, which I'll call x and y. Okay. So we can see here that the Feynman diagrams, when you think about the path integral point of view, arise in a very natural way just by taking account the combinatorics of this integral. And you should really think of the Feynman diagram expansion as literally a perturbative expansion for an integral. And it's a perturbative expansion for an integral that you can't do in terms of a bunch of Gaussian integrals. Because we know how to do the free theory, the path integral is a Gaussian integral, and in the interacting theory, we just expand order by order in the coupling constant, and in each order, we're just computing a bunch of quantities in the free, that is theory, by doing some Gaussian integrals. Okay. So, indeed, because of this, you might suspect that Feynman diagrams would be useful even when you're calculating normal integrals, much less path integrals. And if I have my act together, then the problem set that I'll hand out on Thursday will give you an example where you'll actually use Feynman diagrams just to compute some normal integrals. Okay? And not only will that be useful for computing integrals, it'll give you some great intuition for how we calculate Feynman diagrams more generally. Because all of the combinatorics, all of the symmetry factors, stuff like that, which appear in sort of hard to understand from the diagrammatic expansion, it's just properties of integrals. Okay, it's just tricks for doing integrals. So I'm out of time. Maybe we can just continue next class, and we'll sort of wrap up our discussion of Feynman diagrams. Okay. See you on Thursday.